Thanks, Guy. So now we are welcoming Francesca McDonald from ESA. We'll talk about the first ever gas extraction of an Apollo lunar core sample as part of the ANGSA program.
Good morning, good afternoon, good evening. Hope you can see me. I'm trying to share my screen.
Yes.
See it?
Yeah, all good.
Lovely. Okay, thank you. So yeah, I'm here to a bit of a gear change from all these wonderful detailed laboratory experiments. I'm very jealous and very impressed at the same time, but I'm going to focus a little bit more, bringing it back on how do you get those samples to your lab. So looking a little bit at the sample return chain, and in particular within the context of the ANGSA program. So it's been quite an exciting event that happened earlier this year. It's been a lot of planning by a hugely international effort. And it's been the first ever gas extraction of an Apollo lunar core sample. So as we're looking to moving towards going to these polar regions, which is clearly a lot of interest, there's also an interest in targeting some of that volatile history as well. So we can really learn from this, as well as getting great samples and great science, feed lessons forward to how we can start to handle some of these more volatile rich samples and preserve them so they're pristine and well kept for these great analysis that is being done internationally. So I'm presenting on behalf of ESA, where I had a role at coordinating the science requirements and the curation requirements, these really stringent rules around preserving the samples, and feeding that into a team of engineers and working closely also with the Washington University St. Louis on how we can create a system where you can actually extract sample gas from a solid sample to be able to sort of from the headspace of a solid sample that this can now be analysed. So it all stems from the fact that Apollo planned for the future, especially creating a suite of pristine samples, and with the foresight that there will be advancement in analytical techniques. So there's these samples were curated in a different way to normal. Some were kept unfrozen, some were kept in a different inert gas, helium, as opposed to traditional nitrogen. And in the case of this sample I'm going to discuss today, there's one that was kept vacuum sealed. And instead, this being discussed in the context of the Apollo Next Generation Sample Analysis. This program incorporates a consortium of 9 international science teams, but that also has the curation, the Apollo curators, engineers, and international space agencies involved. And the whole point is so we can address some key outstanding lunar science questions, particularly on lunar volatile behaviours, and in the case of this sample, to understand the history of the Apollo 17 land site. But as I said, there's lots of lessons that can be learned about future sample return, containment, and can all feed forward to next generation volatile rich sample return, whether that's Artemis or Mars sample return. So in particular, the sample we want to look at is one that was a double drive tube core, and the lower segment itself actually hit about 70 centimeters below the surface, and it was dug out from the light mantle avalanche deposit at the Taros Littrow Valley. I don't know if you can see my cursor there, but it's where it says 73001 on the right there. And running sort of across the valley there on the landing site is a fault scarp, the Lee-Lincoln Fault, and it's hypothesized that gases may be released in this fault and trapped within where this sample was taken from. So this specially vacuum sealed sample provides a prime way of perhaps addressing this key science goal for Apollo 17. So just to iterate that again, you have this double drive tube hit into the ground, and the upper segment was kept pristine, but that was actually open last year, but the lower segment remains sealed under vacuum and up until the beginning of this year. And it's purported that the depth that this sample came from, it might have been about 250 Kelvin. This was a study by Keeman Langseth, which conduces the preservation, perhaps have some of these loosely bound volatiles to be sampled for the first time. So this sample was sealed under vacuum at the surface of the moon, but it was secondly sealed again when it got returned to the Earth in an outer vacuum container. So we're going to use the word CSVC for the core sample vacuum container and OVC for the outer vacuum container. So we created a gas extraction setup. So this was partly a extraction manifold that worked under ultra high vacuum. This was designed by Washington University St. Louis, and it was very similar to the sort of the workbench setup that you get for gas analysis, mass spectrometry. And as part of that, there was lots of canisters there collecting gas on there. There was lots of pressure gauges to observe the behaviours of the gases as we're extracting them. And there was also a quadrupole mass spectrometer there for some residual gas analysis. And then attached to that was this piercing tool that ESA designed. And this whole setup is to allow for precision piercing of the CSVC base to extract gas carefully before opening the sample. But we don't want to pierce a Teflon cap that's holding the regolith inside in the drive tube. And we also want to avoid any fractionation of the gases or introducing any contamination. So there's a lot of challenges to be addressing as part of the design here. And it was all bespoke design, built and re-stringently tested and cleaned at the respective sites. There's more information about that in the abstract, and it has been presented previously. So I'm going to move forward to the actual main event. So first of all, it was sampling that outer vacuum container. So when it was brought out, we looked at it, because everything that we'd had done had to be done based on documents before. There was no accessing the sample. It was preserved in a nitrogen glove box in this outer vacuum container. And when we tried to connect it, we realized that actually there was not a compatible connector. So we actually had to cut the connector off and use a compression connector. But stringent helium leak testing showed that this was a viable way forward, and it really worked. But there's lessons to be learned about how you work interfaces in the future. So line blanks were taken, very important to get your background established, and then the manifold pressure was able to achieve an order of times 10 to the minus 9 torr or times 10 to the minus 8 millibars. So really achieving these ultra high vacuum pressures to enable a passive movement of any gases that may be preserved in there outward, because to preserve the pristinity, we really didn't want to be shaking or introducing any thermal gradient here. So the first extraction of that gas occurred, and a pressure was observed on the gauges of about 28 torr. That's 37 millibar. And that sort of order of pressure is largely consistent with the pressure that that outer vacuum container was evacuated to at the time it was sealed. So sort of giving us an idea that it's actually really done quite a good job there as a first sort of order of hypothesis. And a few more samples were taken a little bit over time. We started to see a small drop in that pressure as we started to collect, but also you need to account for certain offsets of the additional volume of the canisters that you're introducing. And when we looked at the spectra, we started to notice that it's dominantly nitrogen and hydrogen for all of the samples. But you would perhaps expect this if it's been if it was closed within a nitrogen cabinet, and if you're going to be getting hydrogen gas degassing from the lot of stainless steel that's in the system there. And additional test aliquots of 100 cc were taken, so initial laboratory analysis can be done. Once the OVC was disconnected, the whole system was baked out, and we started to have a look at what was in there. So this is the first revealing of the CSVC since it had been sealed, and this has all been done carefully in the nitrogen glove box, and you can see the OVC being open there, and this is the first time we get to see that CSVC real, and it was really good to see that it looked exactly like all the documents that we've been working to and all the dummy models that we'd made up and been testing to. But before we wanted to go ahead, we wanted to really check that there was no nasty unknowns in there. So we triple bagged this core sample vacuum container in Teflon, and it was taken to be XCT imaged at JSC. So we looked for any potential unknowns. There was nothing too nasty there. We wanted to check we didn't have any real big dust problem that may mess with valves within the vacuum system. But we're really interested in how close the Teflon cap was to the base, because we really don't want to pierce that Teflon cap. But when we looked, we saw it was flat against the base. So this was our worst case scenario, but it had been very extensively tested for, so we weren't too worried about it. But you can see through the image there, perhaps the clearest one on the right hand side there, you're seeing that grey bases. That's the Teflon cap around the bottom. So we know we had tested for this, but we're not sure how the aging or the flight radiation exposure may have changed the brittleness of the Teflon that we were using to test. So this was the only slightest unknown that we had some concern over, but we're more than happy to start pushing ahead. So the CSVC came out with its Teflon nappy in the nitrogen glove box there again, and it got introduced into the piercing tool that had been bespoke designed at ESA. Because we were worried about tolerances and it not fitting, we'd done a lot of testing to the maximum tolerance, and actually the CSVC ended up to be quite narrow. There was a little bit of an offset there, but actually the tool design had very carefully accounted for being able to hold that and keep it very secure, so that there was no offset or torque and no risk of opening up leaks as part of this sealed system that the ultra high vacuum system had to work under there. So it's there's Juliana Gross there, one of the curators, doing an incredibly delicate job of manoeuvring the CSVC into the tool. And between us, we secured it in there. We also had to think about some of the logistics of when you would lubricate the valve, because you do not want to be doing that in your pristine cabinet as well. So we had a bit of a blind flange swapping and dancing around system on the go as well. It had all been very planned out with everybody involved in advance. So then it all came out of the glove box and everything. This was the first time the setup became united as a full gas extraction setup. So there's just a few images there. And you can see Ryan Ziegler there for scale on the right, showing you the whole system set up, the piercing tool on the right and the gas extraction manifold on the left there. So now it's time to start looking and checking out, is that CSVC leaking? And more importantly, is the tool that we put it in leaking as well? So we pumped everything down, we got it down to a nice high order, low order of times 10 to the -9 torr. But then when we actually opened the system to the piercing tool, we started to see a jump in pressure. And this was a little bit of a worry. So we looked at the residual gas analysis. We could see a significant increase in the nitrogen and hydrogen peaks compared to the original background. So we expected that you would have some of that nitrogen around from the glove box, and again the hydrogen from the gassing the steel. So we did significant helium leak testing, and it was pretty certain that there was no atmospheric leaks. And we left the whole system evacuating overnight to try and bring that pressure back down, let it stabilize. But we're only actually reaching around 10 to the -6. We never hit the 10 to the -9 again. So additional helium leak tests were done, but we're still seeing quite a high nitrogen peak there. So at this point, we started to come up with some hypotheses before we figured out how we would move on. So hypothesis one, that the gases from the stainless steel walls, which might be saturated with nitrogen and hydrogen, or there is a chance that that CSVC could be leaking, reserving a mix of the outer vacuum container nitrogen and the inner CSVC lunar gas. We went for the most conservative thing to do. We closed everything off, isolated from the pump, and we checked to see what the rise in pressure could be. And we could see that it was enough of a linear leak rate to indicate that we could be having a leak there. So we still wanted to collect that sample. There's still important information there. There could still be lunar gas mixed in, so we made sure we sampled that. And then we isolated and evacuated the manifold overnight. And then just before we were going to go ahead with the piercing, we collected whatever gas had been brought overnight as well. So we never dumping any of the gas if we could avoid it. But we still wanted to make sure we had a good enough pressure difference to be able to be prepared for the CSVC piercing. So we were able to then really pump the whole system down with the piercing tool and the CSV isolated to times 10 to the -9 torr. And then we went for it. We went for the pierce. And you can see me there with the torque wrench as we're slowly manually operating the tool. And then we've heard a delightful audible pop. It didn't always happen in the testing, but it did in this case. It's a very satisfying pop. And you can see the top right there, lots of happy people watching the pressure gauge. That was quite a theme of the week, watching a pressure gauge there. But that was a happy time. And we're able to take samples, and we kept monitoring that pressure. We could see it jumped right up to 4.5 to 5.9 millibars. So there was a lot of pressure gas coming out of there and filling up those cylinders. But then it was left to do long extraction. So over the order of 7 to 10 days, we took 2 longer term samples, because all the shorter ones had only been over a period of 15 minutes. So we're really letting it sit there and letting it just slowly diffuse out over time under the lower pressure, just under the pressure gradient. So we tried to extract as much of the gas that we physically could without being able to apply any agitation or heating. The final sort of hypothesis we got from this week of just staring at pressure gauges is we think the CSVC may have leaked. We're pretty certain the outer vacuum container did not leak. So in there we have preserved the gas. It could be a mixture of the lunar gas and the nitrogen from the OVC, but this is where the fun now starts. We've got the samples are out there. They're being analysed as we speak from the test aliquots. We've got general composition going on at the University of Mexico, led by Zach Sharp, and noble gas isotope analysis going on at Washington University, St. Louis, led by Rita Parai. And that's really going to show some diagnostic ratio measurements for the presence of lunar gas, particularly looking at some of those neon and xenon isotope ratios there. And then subsequent detailed analysis of the gas will commence after that, and it is anticipated that gas samples will be made available to the broader planetary science community via an open call by JSC, perhaps later in the year. So that's to be confirmed, but do look out for that. And since then, the solid regular sample has also been extruded and undergone dissection and allocation. So just a quick flip back to the performance we've seen so far. This is all quite recent still, so we haven't done detailed analysis, but to a first order, the first XCT images and optical images of the base of the CSVC, it shows that the piercing tool that ESA worked on has really actually performed as it should. It's made an ample hole for free passage of gas and likely not to have induced fractionation. Didn't pierce that Teflon cap. We had no clue until the sample came out. We just had to go with it. So that was a long wait to see whether that Teflon cap had been pierced or not. You can just sort of see the grey deflection of it there, but it stayed intact. The metal piercing tab as well, that did not come off, so it's limited the risk of contamination there, and it doesn't appear that there's been shedding or flaking of material, but there's lots more follow-up analysis to do. Anyway, I won't prattle on too much, but there are lots of lessons learned, there's lots of findings that is coming out of this. There's a big long list here just to pick out a few. We now have got this baseline procedure, set of requirements established and demonstrated for such an event, and this is all leading to hypotheses that can be tested for new science and can really feed forward to events such as Artemis and Mars sample return. And it just shows the major benefits of international collaboration. International agency cooperation has also been demonstrated, including establishing a hardware loan agreement between Johnson Space Centre Sample Curation Facility and ESA. So we're really starting to see some of these collaborations moving forward to the next generation of exploration. But there's lots of other lessons learned in terms of how we develop the hardware. So we really were only working from documents, although they had phenomenal documents, there was missing information. There were certain assumptions that had to be made and worked to. So we really do recommend things like producing physical duplicates and high accuracy digital twins of flight hardware and their interfaces. And also really exploring how flight hardware may degrade with time and during flight, because that was the uncertainty around the Teflon cap. But a big take home is also the really early definition of mission goals and sample selection, all in consultation with science teams and curators. That really provides clear driving requirements for good hardware development and being prepared for these events. And really important is to really consider the whole lifetime of containment, not just at the point of collection. It may have made this a whole lot more simple for getting the gas out of the can, but first of all, I think that we should be getting some very good science out of this soon, and I urge you all to be looking out for EPSC and also an Apollo 17 ANGSA workshop that's coming up at the end of the year. Thank you.
Thank you, Francesca. A very interesting talk. I think now we all want to hear about the scientific results out of it.